So this cycle is an ideal Brayton gas cycle, air standard. I say ideal because we have not included any irreversibilities yet, and other than the heat transfer not occurring at a constant temperature. So let's introduce some other irreversibilities, and I'm going to focus here on the TS diagram so you can put this in your mind, and we will scroll to the next page. Okay, and two ways we can represent some of the nasty irreversibilities in real life. One of those is with the heat exchangers. Those involve piping that carries the fluid, the air, and you're learning in your fluid mechanics class. Air has viscosity. Viscosity of flowing air causes pressure drop, and that pressure drop robs us of useful mechanical energy potential. So if the solid line here is an isobar, a line of constant pressure, going from state 2 to 3, I actually would drop to a lower pressure. Similarly, 4 to 1, instead of being at a constant line of pressure, I have a pressure drop going from state 4 to state 1. Another set of irreversibilities would occur with the compressor and the turbine, and we've already learned how to deal with those through our sort of catch-all term, the isentropic efficiency of those components. So just to rehash that again, the isentropic efficiency of the turbine is defined as the specific work that you actually get out of the turbine divided by the specific work you get out of the turbine if it were isentropic, reversible. So looking at state 3 to 4, well, state 3 to 4S represents our isentropic turbine performance. And then in reality, our turbine exits at the same pressure but at a higher entropy, representing the irreversibilities. And we draw that as a dashed line because now it's no longer quasi-static. We don't know the path. Similarly for the compressor, the isentropic efficiency of the compressor is defined as the specific work it would take to drive that ideally if there were no losses due to heat transfer, mechanical friction, those types of things. And then in reality, it takes us more specific work to drive the compressor to overcome those irreversibilities. So on the TS diagram, we've got the isentropic work needed to drive the compressor from state 1 to state 2S. And then in reality, we're along that isobar, but at a state of higher entropy, representing the effect of all of those irreversibilities. Now let's look at a couple of interesting examples of how Brayton cycles are used. One would be a jet engine. If you've ever flown in an airplane, you're familiar with the Brayton cycle. So conceptually, we can start at the top left here, and we see the compressor compressing the air as it comes in. We inject fuel in combustors and ignite that for combustion, which releases chemical energy from the fuel. And then that higher energy fluid expands over the turbine, and then the reaction products are spewed out the back. And we conceptually attach to the front of the compressor what is a diffuser, devices again from back in chapter before when we learned different control volume engineering devices. So a diffuser is a device that exchanges the flow energy with a kinetic energy change. On the back end, we have a nozzle. So moving to the image on the right, we've got our compressor, combustor, turbine, and then they show a diffuser connected to the compressor and a nozzle connected to the turbine. The TS diagram has state 1 to 4, so this is state 1 and 4, similar to what we've been working with. So this would represent atmospheric pressure, and then the act of the nozzle and diffuser essentially drops us below that. If we look at a plot of compressor ratio, okay, again, this is our compressor ratio on the x-axis, and then the the arrow on the left here points to the net work produced for this per mass flow. In other words, specific work. And then this curve references to the axis on the right, the thermal efficiency of the cycle. And we have some competing things. If I wanted to make this cycle more efficient, I would increase the compressor ratio as high as I could get. But the interesting thing happens for a jet engine. Usually those are attached to airplanes, and you have to lift that mass into the air. So you want to get the most bang for your buck, the greatest work you can get per unit of mass flow, and you see a design point to minimize that somewhere right around here. Okay. So one example of the Brayton cycle flying in the air is the jet engine. Another example, and this is actually your homework assignment, which is posted online, is called a combined cycle. And I'm going to actually explain the combined cycle and then also cogeneration. I think this is pretty cool. The world record for thermal efficiency for a power plant is right around 60%. I've got several real-world examples on the course website if you're interested to read some of those. I believe the record holder is by a company called Siemens out of Germany, and it utilizes, by combined cycle, we mean a Brayton gas cycle connected to a Rankine vapor power cycle. Let's see what we mean here. So the top cycle here is our Brayton air cycle. With the jet engine, using air as your working fluid, you can usually run much higher temperatures. So the downside is your exhaust coming out of the turbine here is at a relatively high temperature compared to the atmosphere. Being at a high temperature, we realize we still have the possibility of converting a good amount of that to work. The second law tells us that. So what we do is we pass the air through what the book is calling a heat recovery steam generator. That's just a heat exchanger, control volume device that is then connected to another closed loop, which is a Rankine cycle. So we have air as our working fluid for the Brayton cycle above, and then we have some sort of fluid that changes phases. So water or refrigerant, ammonia, anything else along that nature that's going to have a phase change. And we drive our Rankine cycle. Okay. We can view this entire thing as a closed system if we, let's see, I'll close the Brayton cycle. So we have a closed cycle of air there. Below it, for the Rankine cycle, we have our closed cycle of our working fluid. So this dotted line over everything indicates our control system. And we have a rate of heat transfer coming in. Again, this is our combined cycle. And we have work produced on two sets of turbines, the turbine on the gas cycle, the turbine on the Rankine cycle. So those then add together. We would pass them to a generator and use that to produce electricity. And again, these types of devices are the world record holders somewhere around 60%. I think they've gotten just a little bit above 60%, if I remember correctly. Okay, the first law, or the second law, still tells us we have to reject some energy to the atmosphere, and that's done by the condenser of the Rankine cycle. So I have two options. One is I could just reject that to the atmosphere as normal. That's one option. The other option is what makes this called cogeneration. So a lot of times we need a heat source. It could be we've got a college campus with a lot of centrally planned buildings, and we want to heat them in an efficient way. It could be we're next to a factory. That factory uses a heat source for some sort of production process. But what I can do in that case is have another cooling loop that takes the energy out of my condenser. And then that other fluid loop then goes from liquid condensate to steam, and that steam is then used for some sort of process or industry. So again, this is called cogeneration. The downside here is that the requirement of having steam in the cooling water limits your condenser pressure. Also known as back pressure. The other thing I'll mention here is that the heat recovery steam generator is just a heat exchanger. So we can apply the first law. It's the only different looking device than what we've covered recently. So the first law on the control volume of the heat exchanger. Again, this connects to section 4.9 back in your textbook with the usual assumptions that I've been working with. Negligible heat transfer, negligible work, energy being brought in by the fluid through internal energy and flow work, and energy being carried out by the fluid. And so we can expand these terms. And the thing I want to point out here is that you have two different fluids. So we have the mass flow rate of air coming in, state 4. We also have the mass flow rate of, I'll call it the water, state 6, and then leaving mass flow rate of air, state 5, leaving mass flow rate of water, state 7. Again, I say water generically. Obviously, it states 7. I realize I need to have steam to go to my vapor power cycle turbine. And then if I want to, I could simplify this algebraically. And then I realize on the left-hand side I'm dealing with air, so I would model my enthalpy change using air information. On the right-hand side I've got my steam cycle, water, so I would analyze that using my steam tables. Okay, your homework assignment will look like this. It will not have cogeneration. It's just a combined cycle, and I know this looks like a lot. Before you kill me, the problem gives you the state information, so you'll have to analyze, I think, the heat exchanger, but you've got all of the tools. This is nothing new, essentially. This is just combinations of the pieces that we've already learned. You can do this if you just start, work your way around the system, analyze component by component, and put it together. You can do it. The last thing I'll mention, I'm not covering this, but I've got a link to a collection of other gas cycles. The Stirling cycle is one example of a external combustion gas cycle, meaning that the hot end you see here, that high temperature would be due to some sort of heat source, combustion on the outside, heating the air on the inside of the piston cylinder assembly. This is a pretty interesting cycle. It has quite a history attached to it, and there have been a few people trying to make progress with Stirling cycles in the last few years. I've got a couple links on the course website, and just a couple Google searches will open up a wealth of information for you as well, if you're so inclined to have a look. Okay, that's it for gas cycles. Thank you very much.